Good morning, everyone. Everybody ready for one more day? Okay, so we're switching this around. You can see we're skipping to slide 152 here. The end of the day. We're going to start today, I think, by talking about large loads, and then we'll skip back to talking about system strength. So probably might not get done that before lunch, and then after lunch we'll do a few more smaller topics, system studies, a little bit on DER, and then we'll finish with grid forming. Okay. So this is the topic, right? This is in the last 2 years, 2.5 years, I would say. The first time I saw one of these large load profiles was about 2.5 years ago for one of our customers. They showed it to us. And I basically said straight out, you know, that's not right. You didn't measure it right. And we went back to the loads and pushed them and said, no, this is actually what we measured. This is what's coming out of the plant. It would just be scaling up. And then if you fast forward about a year, I was convinced, no, this is actually what they're going to do. But I was also convinced that they're doing it wrong, right? You're doing it wrong. Stop doing that. This isn't, you know, this is a silly way to do your loads. You should change your software. So now, present day, we've got loads in, and I've been convinced that they're not going to change quickly. There are good reasons, I suppose, for what they're doing, and this is how it is for now. You know, it's going to change, but for now, this is what it is. So I want to start by giving you just a bit of overview on, and again, this is from the perspective of studies and modeling and planning, right? So we're actually in this context not that worried about what they're doing with their load. Maybe we are as people or as, you know, holistic human beings. We care about AI and all of that stuff. But right now we're worried about how to model it and how it's going to impact our grid. So I'm going to bucket these loads into a few kind of large categories. The first type of load we'll talk about we'll call it hyperscale cloud data centers. So we're talking about data centers here. These ones are essentially resources for shared use across the internet. They're not actually very new. You might find these like AWS has some of these, Google Cloud, Amazon Shopping if you're watching Netflix, if you're watching other streaming services, Office 365, Google Search. And these ones are highly reliable loads. So now what we care about for modeling and studies is how do they touch the grid? So what is the what equipment is connected to the grid, right? And then we can figure out how to model it. So they're cooled by variable speed drives. Sometimes they use active filters for harmonics. They have all of their IT infrastructures behind highly reliable equipment. So things like a UPS will be very common. UPS backup and generator, diesel generator backup. And then they have some office and admin computing. These ones aren't as large. They tend to be, you know, tens to hundreds of megawatts. Probably not that even big. Tens of megawatts is typical. And then we have crypto mining. So this is another bucket of load. It's a different type of large data center load. These are owned by private developers. They tend to come up very quickly because they're a huge box that you put in rack after rack of PCs. Basically, they're special PCs, but they're essentially a PC with a power supply directly connected. They don't have a generator backup. They don't have diesel backup. They don't have UPS. They don't even have often active cooling, or they have active cooling but no sophisticated cooling. It might be as simple as fans on the side of the building. They even arrange them in a way that, you know, the wind coming off the mountains might cool their hardware. If they trip, they don't care. They just restart. And so that's crypto mining. And then we have AI inference models. So these ones are data centers that are essentially addressing distributed user requests for AI. So if you make a input request to ChatGPT or Gemini, or your phone is doing something with AI, then it will be accessing one of these servers, and they're basically dealing with thousands or millions of individual requests, and those are accessing trained models, so pre-trained models. These ones can be very large. So these ones, hundreds of megawatts up to more than 1,000 megawatts. And the interface hardware that they're using now, actually, they take a step back sometimes in reliability. They do care about reliability, but I've seen some, for example, recent ones from press releases from Microsoft showing that they're actually depending on, they go into extremely highly reliable grid locations, relying on the grid to be up, and they don't use necessarily UPS or diesel generator backup, which means that the interface to the grid might be power supplies again, okay? But they might be customized power supplies, much larger power distribution units, or customized highly efficient power supplies as compared to the Bitcoin mining or the crypto mining hard power supplies. Okay. Then we go to AI training, and this is essentially could be exactly the same facility as the AI inference training. So it's the same hardware, the same sizes, the same owners, but now they have this special feature, which is a variable active power output, which is what we've all been sort of concerned about and we'll be talking about a lot today. So the reason why I'm distinguishing between these is because if you have a large data center coming in, what you have to worry about and how you're going to model it is going to depend on what the data center is ultimately going to be used for. Some of the folks that you talk to who are going to be building data centers don't actually know. They might be kind of an intermediate developer type who wants to develop the capacity for a data center, and they're trying to sort of secure the power and make sure that the infrastructure to the grid is connected, but they don't actually know what kind of load is coming in. But it really does matter if you want to model it ultimately. Even if you're talking to a hyperscaler directly or somebody who's going to be actually building the load, that those plans may be changing all the time, whether it's inference or whether it's training. But sometimes they do know, and that can drastically change what you're going to do with that load or how you're going to study it, how you're going to connect it. Very quickly, what does an AI load look like? This is public information. Everything I'm going to show you is basically public. This is the Colossus plant when it was 250 megawatts. It takes about 200,000 GPUs for this size. This was Tesla built it very, very quickly, 120 days. Uses 2 million gallons of water per day, estimated, and cost an estimated $10 billion. Okay, so this is a significant amount of money and water. The water issue kind of hit the news, right? Some of you might have seen communities nearby, not necessarily this one, but others, having problems with water. And it's a really bad look. And so the latest data centers are using significantly less water. I saw, this was just a couple of weeks ago, I saw a press release by the one going into the second version going into Wisconsin, and they have another one down down further south, and I don't remember which one it is, but this was Microsoft press releases, and they were saying they're using now closed loop water that gets refilled or replaced every 6 years or something, and it's very, very low. Yeah, question. The cooling, yeah, for water for cooling systems, exactly.
They're open air chillers, like basically waterfall type swamp.
I don't think so. What? I don't know what that is. Sorry.
It's like evaporative.
Okay.
Yeah.
Is it? Okay. I don't know a lot about the cooling system.
Bring it over, so. Yeah.
You had a question?
I would just too many gallons of work today. That's not, they're not. I mean, is it like a once through cooling concept or dumping it somewhere?
It must be. Yeah, I don't know. Yeah. Yeah, right. Yeah. This is what it looked like inside, and there's new pictures of the bigger ones coming in. To me, I was surprised at how small this actually was in footprint. I mean, some of these are essentially the same load as a medium or large size city, and and they're not physically that big. They're very dense, and now they're building them 2 stories, so they're even more dense. Okay, I don't know a lot about how they're actually built and constructed, so I'm not going to talk much more about that. Um, but we are interested in reliability risk, right, and in studies. So there are a number of categories of risk that might drive requirements or studies. Okay, and I'm going to always be saying requirements and or studies because one of them can kind of, to some extent, alleviate the need for the other. If you have a very tight requirement and good enforcement of the requirement, you may not need to do a study, and we'll talk more about that. So here's the basic sort of categories of risk. We have the basic power flow considerations, right? So when you're building a big load, you have to worry about the normal things we worry about in power flow. Do you have the voltage and the thermal capacity? You're going to take your lines out, different operating conditions, different base load conditions, and make sure you conserve the load. So we won't talk much about that because it's relatively straightforward with a few exceptions. Active power variation is a new one and a key one. So now we're worried about synchronous generator damage. We're worried about flicker. We're worried about machine mode oscillations and inter-area oscillations. And I think I have a, just skip ahead here. I don't have a slide here showing the actual, I got the wrong slide. I'll just draw it for you. So what we're worried about here, and this was published in a recent paper, not even so recent, but you have your, no, it's not coming to draw on here. I think I have to leave, so we have our time and our power. And what we're worried about with these training loads is essentially we have some load like this, and it dips down, comes back up like this. Some noise, dips down, comes back up like this. Okay, and this might be 20 to 30%. So let's say 30. Say 0.3 per unit, and 1 per unit is up here. Okay, so this can include frequencies like the period. This is what I would call a quasi-periodic variation, and the period of this variation could be between, say, half a hertz or 2 hertz, let's say 2 cycles per second, up to 10 or maybe 0.1 hertz to 2 hertz, something like that. So dipping every, twice a second all the way up to once every 10 or 20 seconds. And maybe, you know, even beyond that in some cases, but that's what we've seen typically from the measured data. And then the frequency content on top can vary. Yep.
You're saying that the active power load from these data centers actually can get like 30%, pretty sure.
70% or 80.
Such like high fidelity.
Why would they demand?
Asking for like, you know, 0.999.
Right. Yeah. 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 So what I'm gonna do this morning is sort of avoid the why questions a little bit. Okay. And then we can talk about why questions at coffee. Yeah, but that's the you know, back 2 years ago, this is sort of the questions I was asking too, like what, you know, what is going on? Yeah.
We've been told 5 times.
5 times a second, so even more frequent.
But you said measured, so this, you got this kind of data measured.
Yeah, we've seen measured, and actually there's some that's been published now. You can see various sources of published data that show it. So what these are, sometimes these are test power. A lot of the data centers that are coming in, they're actually under construction to greater than a gigawatt, but we don't have any that are that big yet. We have 200 to 300 megawatt and bigger. The ones that are coming in at 1,000 will have test power at 30 to 100 megawatts, let's say. But it's just a complete scaling factor. It's going to be exactly the same profile. Yep. And a lot of it is from slightly smaller, I would say 30 megawatt. Yeah. And then lots of test data that's done in sort of a lab behind with the equipment before they install it. So I thought I saw another question. Yeah.
Is this only for the shape is for AI training or?
Yes. So exactly. This is a characteristic of the AI training. If it's inference, it's not. And the reason for this, and I'm not an expert on the reasons for why they do this. So I'll try and answer just a little bit of the why from somebody who doesn't know about AI, okay, simulation engineer, but they have essentially they're distributing their training. They're trying to train one of these large load models, which uses billions of parameters. So they're these huge parameterized problems that they then distribute across these hundreds of thousands of GPU cores, so simulation cores. So they send parts of the problem to all of these different CPUs, and then at some point they need to collect all the data and do a synchronization of time. Basically, they need to bring it all together into the common problem again, and then they have a data transfer sort of time, and that synchronization is very difficult to avoid. And so that's what causes these big dips. But in between, there's lots of stuff that happens. You can see different frequencies that show up and different magnitudes. Sometimes we've seen this number be, you know, more like, you know, the top of it look more like this. And then the overall period of this process can vary a lot. So, and one of the things we'll talk about a little bit more later, but that you need to realize is that all of the recorded data that we've seen from these things and that anybody has seen, the data centers themselves don't know for sure what the next set will look like. So you can't assume that just because they gave you a recording of what it looked like in their measurement, that's what their data center looks like. Okay, that's what it did look like one time. But the next time might be quite different, and they actually can't tell you because they don't know. And so one of the mistakes I've seen planners making is to basically, and this is a very reasonable question, I think, what does your load profile look like? That's the question you ask, right? What does your load profile look like? And they'll give you some example load profiles, and you say, okay, and the manufacturers will do this. If you're asking for a mitigation, like an ESTAT or something, they'll say, what are we designing to? And you give them these sample recordings, and then they're quite happy, and they design and show you a nice energy sort of equation that meets this demand. And you need to be aware that that was just one example, okay? And there are many, maybe an infinite number of other examples that could happen. So the question, what does your load profile look like? Just be very careful with that question. If you're asking that question, you have to realize they're going to give you examples. So what your better question might be, what are the boundaries of what your load profile could look like? Okay, what frequencies, what's the highest frequency you might encounter in this load in the future? Because there's going to be a roll off at some point. Or what does the variable portion of your load look like? Things like that. So just be very careful with, if you're getting recorded data, you might get very high resolution, beautiful data. That's just one example of any number of examples that you could get in the future.
Can I add a couple of things? I
Yeah.
think the way you described it to me, the variation, which was really simple because it was for me to understand, was you can think of the high demand as the actual training, and the low dips are the sending, the transfer of data. So the really simple is transferring data is less power intensive than actually training. And that's where the dips are. So like, if you really want to simplify and think about it simple, like I like to think about it, is just like sending an email is not a lot of data, but like actually training and writing the email is a lot of effort, right? If that makes sense. So the other piece is, like Andrew was mentioning, is for folks who follow AI and like the whole hubbub when new algorithms come out and everything changes, and maybe you don't need all those GPUs anymore. Every time someone makes a new AI algorithm or a new language model or something, this load profile is going to change for training.
Right.
Every single time. And then the other kind of weird analogy that I'm trying to use, and people can poke holes in it, is my mind, it's similar to GMDs, like geomagnetic disturbances. The variation in the load, right? Because every solar flare is different, every magnetic storm is different, but you can kind of get a feel for what the worst case magnetic storm would be. And then in the similar vein, we should be able to, or maybe we should start asking for a worst case training model, right? Like what is the absolute worst fluctuation in period that you could get from your training model? And then you can plan for that. And then if you're within that benchmark event or benchmark profile, then you have planned at least for the more severe one.
Yeah.
Which is okay for magnitude, right? But then as the periodicity changes and stuff inside there, then all other problems come. So it won't fix everything, but a benchmark of magnitude could help, or just a way to give planners something, because planners like to pick 1 second out of a whole year, right, and study that. So how to transpose this super variable thing into that one peak second.
So we'll have a few more examples of what you're talking about using worst cases, but so yep. Yeah, we'll talk about harmonics. Yep. But this is not harmonics. This is like active power forcing functions, right? At a much lower frequency. Okay, let's carry on. Keep asking questions. So with this active power variation, if this is what's happening, we're worried about synchronous generator damage, and we'll talk a lot about that. We're worried about flicker, right? This is going to be bumping the voltage pretty hard. We're worried about machine mode oscillations. So if this happens at, let's say, 1.5 hertz or 1 hertz, something like that, we're now at a fundamental frequency machine mode. If this is happening at 0.1 hertz or 0.25 or 0.5 hertz, and you're forcing this function at a fairly large level, those are inter-area modes that we can be potentially driving, right? So if you're going to do this for a while, you can potentially excite an inter-area oscillation. Ride-through failure, we're worried about, we'll talk a lot more about ride-through failure, but if you imagine this load just dropping off, we are concerned with load rejection over voltage. We talked a bit about that yesterday. We're concerned about VAR adequacy. There are some dynamic VAR considerations we're going to have to worry about, and also resource adequacy. Do we have the spinning reserve basically and the margin to be able to deal with that? Alex, did you have oh no, you're just leaning forward. And then passive damping. Those of you who've been in the IBR world near series compensators or series capacitors know that we're quite worried about the damping characteristics of controllers, right, of electronic interfaces. These are also voltage source converters in some cases. And so if it's a UPS interface to the grid instead of a, type 4 wind or a type 3 wind interface to the grid, it's still a voltage source converter, power electronic controller, and so we're interested in its damping. And maybe we're going to be starting to move damping characteristics into problematic regions again. So those are sort of the categories of risk. So we're going to go through each one of those and sort of think about what studies we might do or what we might do to contain those risks. So for the basic power flow studies, first we have to ensure that sufficient generation exists, right? And this idea that imports are going to be the answer to your question when power flow studies are being done, a planning engineer will sometimes rely on the imports to be able to serve that, but everybody's looking for generation. So your neighbors are probably also dealing with that. You need to make sure you can serve the full load under outage conditions. This is normal power flow stuff. VARs need to be available to control the voltage for various transfer scenarios, also normal transfer scenarios or normal power flow stuff. But the last one is the VARs are available for fast changes in load. So we're not used to, we're used to things like duck curves or morning peak and afternoon or evening peak, sort of smooth load curves that look like this. And we're not so much used to load coming and going extremely quickly in really large quantities. So if you have 5,000 megawatts of load, that can just essentially disappear and then come back at any time of the day as many times as they want. Now you have potentially a VAR, a dynamic VAR problem, right? Yeah, and one thing, I don't know if I have a slide on this, but I just want to make sure you guys realize, and this was also, I can say this because it was just in a press release, sort of as a flex, that these guys were flexing that they can make their data center even bigger and more powerful by connecting them across regions. And we knew that they could do this already, but now it's public, so we can say they're actually doing the same process. So if you imagine this being a load, in one location, one city, it could be exactly the same process. They're building very, very high-speed communication across geographic districts and connecting multiple large data centers so that they're all doing exactly the same process at exactly the same time. They're all working on the same training model, which for a planning engineer is a nightmare, because now we're thinking you're studying one interconnection, but actually what you're doing is you're studying an extension to another interconnection in a completely different geographic region. Maybe even a different control area, different, somewhere outside of your footprint, or maybe it's within your footprint. But now these two completely electrically, geographically isolated plants are 100% coupled. So everything is working exactly in synchronism. So that's very worrying. So when you're thinking about VARs and you're thinking about the whole plant ramping down, suddenly it might be a much wider area load rejection than you thought.
Andrew, what are your thoughts on that creating oscillations in the regional area or other kind of, what happens if one trips off, with like one data center who's part of this would trip off as well?
Yeah, so what may happen is that one of them, and I'm honestly not trying to fearmonger. I feel like this is,
Well, fearmonger, then we'll get positive. Yeah.
Our job right now is to just try to imagine and contain risks. So, and these are questions you can ask. If one of them disappears or there's a fault in one of the plants, that process is interrupted, they may stop the process for all of the plants, right? So you get a common load rejection. It's not due to a fault or anything. It's due to just the processes all stopping together. I'm going to come a little closer. Sorry, you probably all noticed I have not got very good hearing, so
my question is, you say sufficient generation exists. I imagine we're gonna have a period where there isn't sufficient generation.
Right. We're there.
Planners are gonna have to figure out what those trade-offs are.
Yeah.
That's another dimension.
Right. Yeah.
Flexibility at all, like load flexibility?
In what sense?
Like some loads might not want a firm load. Like if there's some large load developers will like pitch the idea of don't count me as firm load if you get me interconnected quicker. Like that
Oh.
type of flexibility.
And actually, it's been there was a FERC letter that came out that said they wanted to encourage that
Yep.
type of thing,
That's why I
right? So they
asked, yeah.
want.
Which
I
sounds-
wasn't planning on talking about that.
It sounds like a good idea, but it's also one of those. How do you put that into practice, right? Because that's basically the opposite of what regular load interconnection is. Because regular load interconnection is it's firm always, and you better
Yeah,
deliver it.
and maybe it could be a good thing. I mean, if you have a load that's willing to back off in response to, an under frequency or something, that could be a good thing.
And the other, I think, one more fact or one more anecdote, I guess, of these large loads or some of these large loads is that over the period of the whole year, very rarely are they actually using the entirety of their like allotted power, right? As far as the ones that they've been given deliverability for, they're very rarely using all of it. It's usually somewhere around like 60 or 70% of the total over the year of power. But on some days it's obviously this max and ramping or max loads or things like that. So it's really hard to kind of match those resource adequacy on the year basis with your variability and also the day-to-day peak days, what's it doing in that day too. So I think there's a lot of flexibility there.
Well, I think both of what you just said tie each other, which is to say, they move that data, they can move their load from one region to another quickly. So they can say, in PJM, sign me up. You don't have to give me firm power right now at this moment, because if I need to, I'm just gonna move to ERCOT and process it there for the rest of the thing. And so I think those two concepts are related in terms of how those data centers will function. They will pick up the power wherever they can find it. And they can move the trading anywhere that they can find power for those next 4 hours.
Right.
So I think at the beginning of this training, you mentioned obligation to serve loads, right?
Right.
Keeping the lights on for everybody. This load is unique. What is the obligations for utilities, maybe small utilities, serve this loads other than
Yeah.
what's the obligation?
So this is a question I'm probably not going to be able to answer to your full satisfaction, but I think that it's an important question that everybody's grappling with, because we're having to fundamentally, in the space of a couple of years, change 100 years of understanding about load. So up until now, we don't put any requirements essentially on load. We don't have ride through, we don't have frequency voltage control, we don't even have power factor requirements. We just, whatever you do as a load, we're going to make it happen, right? We build our transmission, our generation system around load. And for the very first time, everyone is collectively realizing, sorry, you hit the limit. We can't do that anymore. 100% cannot do that anymore. And so there will be requirements coming, and there will be special treatment of these loads in a way that isn't advantageous to the load. We're going to cost the loads more money. We're going to force them to behave in certain ways that they haven't had to behave in the past. And that's brand new for everybody. Essentially, we're treating these people or these loads over a certain size as a different category of load that we no longer prioritize. We're having to, and we have to do that. That's by necessity. So initially, the reason why everyone's on the back foot and got caught off guard is because we're just continuing to treat them as load, right? But it's really not. It's a new thing in our power system that's going to need whole new processes and rules. So until we get those processes and rules, and we treat them as traditional load, we're in big trouble. It's not going to work. So we're going to have all these problems of retroactive, treatment are going to come up with the loads in the next very, very short amount of time.
I guess I'll add a positive thing, right? at this point, the utilities and planners have some extra leverage right now because there's the way to make money with AI in development right now is to get a bunch of market share very quickly. So there's a lot of willingness to be flexible, whatever that word means, because there's like been full conferences on what the word flexibility means for large loads, because they want to connect, right? So they want to connect very quickly. You want to make sure that they're reliable, right? So there's a lot of leverage on both sides to say, if you want to connect, you have to do X, Y, Z for me. Or if you want to
Yeah.
connect, you must have this type of performance requirement,
Yeah.
or things like that. So,
And
on a
our,
positive note, there's an opportunity for discussion, and it's a different type of world with the stakeholders than it is for IBRs. Like for a renewable firm who's building with stakeholders and stockholders and things like that, it's I want to interconnect as quickly and cheaply as possible. For a lot of these large load developers, I've heard them tell me, just tell me what you want from me and I'll pay for it and just let me connect because I'm going to make money because I have this market share.
Right.
So there's a willingness to have that discussion, but we're not used to having that discussion because like you never have that discussion in a collaborative way with an IVR developer. As soon as you have those talks,
I'll get you in a second.
things get kind of out of hand. But yeah, go ahead.
Yeah, I wanted to just sort of finish that thought. One of the things I will say in defense of at least some of the load, the hyperscaler folks at the end who are sort of driving this, is that like Alex said, they're different in a number of ways. One is in the way they perform and in their size. Another one is in the sheer resources that they have. So they have an immense amount of political power, an immense amount of money, and access to technology and access to technology supply chains that nobody has had before. And so they have both the resources and the sort of the capability to solve problems quicker than anybody has been able to solve problems before. And so, and they want to connect. They also, are human beings and have some, there's engineers in there who are really trying to keep the system reliable and they care and so on. Like, I won't say that's everybody, but there's definitely, good actors in there. And so I think that this idea of collaboration is almost new also for us. So I want to get that question and then you.
So I guess, one, you mentioned how they have all the resources, they'll grow it. I guess in your discussions, on rates, potentially something they're concerned about. Certainly, you have a factory that ramps up and charge more for that heat, and that's their incentive to try to minimize that kind of heat. But it sounds like these guys have all the money in the world, and they're willing to throw.
Yeah, they seem to be. It's a little hard to tell. We all know that they're rich. We don't know exactly. At some point, somebody cares about money in that company, and so they do tend to go to regions where the power prices are lower, and where the power is highly sort of reliable. So they are picking regions and so on. They're not going, for example, to Hawaii, as far as we know, because the power is very expensive there. So they're not immune to cost signals for sure.
Yeah, their equation is speed to interconnection, price of power, and power reliability there. But just to be really clear, we're talking about AI specifically, like crypto mining. Obviously, they're really price sensitive. They really care about the price of power because that's their equation. They're doing is how much does power cost? How much am I making by mining? So this like last 15 minutes of discussion has been just AI compute, AI learning, and AI inference. The Bitcoins and the cryptos are extremely, extremely price sensitive.
There's a different machine behind them.
Yeah.
Yeah.
We're seeing a lot of interest behind generation and also the operation.
Yeah. We'll get into that quite a bit.
The other thing I'll say is for the consumer, I think in Texas, the Data Act legislation that basically tells the operators that they can shut off data centers.
Right.
So
Right.
that's kind of like their option. Yeah, because
Yeah. I see.
Something. There are regions like SPP that are acknowledging all of these trending things, and instead of saying you have to wait 4 or 5 years until we perform a complete resource adequacy studies, let's just try to do this really quick. They are launching these products that they call Hilga. I don't know if you guys
Yeah.
hear about it.
Yeah.
The chill, the one that is actually with conditional, so a lot like, okay, connect here. They are promising like at least, They are taking studies only like as short as 3 months, 6 months connected there, but with the conditional, the chill means conditional, high loads, that could be integrated there. And you have to accept that if something happened in the system, we don't have the way to serve the load, you took down the load and that's it.
Yeah.
It's coming back, yeah. It is, today actually there is a meeting in the afternoon that are going to.
Yeah, they chill, so they had SVP this year came up with a number of products, Hills, Chills, and Hilga. Okay, and so Hills is high impact large load, Chills is conditional high impact large loads, and Hilga is high impact large load generator assessment. So essentially, they made another queue that's parallel to the DISIS, which is their definitive system impact study. And basically, what SPP is saying is, hey, you can turn on this high impact large load on a conditional basis with a path to getting firm in their AQ process or their aggregate transmission studies process. And so, but in the interim, you can go ahead and turn them on. You don't have generation to match your load. So basically, you're going to be served with non-firm. Okay, so now your existing portfolios that are out there are going to have to redispatch around to support the high impact large load, which means that there's a potential for grandma's lights to be turned off so that a data center can continue running. Now, for like the crypto stuff that you're talking about, where it is price sensitive, SPP is also coming up with a brand new product called PALS. So this is going to be a price adaptive load. This is going to be the first time that load is actually going to follow LMPs or locational market prices in the market. And so that'll be different. Today only the generation follows prices in the market, and it redispatches around congestion. But with the price adaptive loads that will support the Infora type loads or the crypto loads, and the load is actually going to move with the prices in the market.
Yeah, I'm gonna deflect us a little bit from the resource adequacy question. And especially from specific utility processes for now, because my concern right now is, like, resource adequacy is important. We can solve market problems and everything, but this is still all imagining these loads are kind of like they always have been, right? So it's a relatively constant load, and we have a lot of other stuff that I think currently aren't being considered with the idea of, let's just turn it on if we have generation nearby, okay? We're worried about a few extra things. So let's get through some of this technical stuff, because I think it's going to inform a lot of these policies, and a lot of these policies are honestly going to have to change once the technical basis is understood properly. So people are coming up very quickly with processes and with ideas for this stuff. We need to make sure that there's underlying understanding of the technical of the equipment is there before we break something with these processes that aren't quite fully baked. Okay, so a quick reminder, this is a slightly technical detour about synchronous generator systems here. So a synchronous generator is connected to a shaft system, which has a set of usually one or more prime mover devices on it, like a turbine. And these, you can imagine these things as, a long shaft, and there's steam or sometimes water if it's hydro, or some kind of a flowing fluid that basically is turning these things. And we have a way of understanding them that is a mass connected to a shaft, connected to another mass, connected to a shaft. And if you remember your physics, and all the mechanical engineers in the room can instruct me on this later, but we're going to have a mass spring system that is defined by those physical sizes and material properties, right? And the frequencies of those oscillatory modes are determined by the physical sizes and weights and properties of the materials. So every mass spring system, or we can call this a generator shaft system, another word for it is a multi-mass system, when we're using modeling language. You can see on the bottom left how this is a cross-section of an actual shaft. We kind of aggregate those masses into simpler, smaller numbers of masses, so it's an aggregated mass. And we can do an eigenvalue analysis on it that determines which frequencies are present in that shaft system and which of the masses are participating in every mode. Okay, so if we start to rock one of the masses at a torsional frequency or a modal frequency, the whole thing will resonate and that will grow, and the amount of energy that you put in will be amplified. Okay, so every mass or every synchronous generator has some version of this multi-mass system, and this has spawned a whole field of problems. Back in the 70s, 71 or 72, there was a series of incidents at the Mojave generator station where they broke a generator shaft, and this was because we had a series resonance in the system from a series capacitor, and that overlapped with a mechanical torsional mode, and the machine started to oscillate at the mechanical mode with the system electrical frequency, and it broke the shaft. Since that time, 50, 60 years later, we now have a long series of studies that we do every time you add a new synchronous generator near a series capacitor, or should be doing. You have, every time you put a new series capacitor in, there's a whole set of studies that need to be done, or should be done. Actually, they do need to be done, not always being done now, but this is old science. So what? If we have a load that is now going to sit there and force the system, the power system, at a torsional mode, there's a quantifiable amount of amplification that will happen in that shaft system. And if you land on a torsional mode, that system will start to oscillate and will grow into a larger oscillation, and you can have torques that build up beyond the endurance limits of that shaft system. Okay, so you can eventually, in theory, you can break a shaft if you continue to do that long enough. So before I do that, I want to add just another slide here. And I've been in many long, painful arguments with generator owners about, or generator manufacturers on this, and there's a bit of a problem we're going to be talking about. But let's just say for now, we use something called, first of all, we'll call this an SN curve. That was a terrible curve. And it looks a little bit like this, where we have, there's different ways to put it on here, different units you can use, but for now, let's use torque. And here we'll use cycles. And it might look something like this. Okay, so this is supposed to be flat. I'm drawing like down with my hand like this. Normally I'm a better artist. I just want you to also know that. Okay, so here, what we're thinking about is for a generator shaft, this is long, well known. If you put a fault on the system, you get a very big spike in torque on the generator shaft components, right? So each of these is designed to handle a number of faults in their lifetime. And you get, let's say this number here, I don't know exactly what it is. Let's say this is 100 cycles or something. Maybe it's probably 1,000 or something less than that, but say 100. So up to here, maybe this is 5 per unit. Maybe it's 1 per unit. I don't know. Some torque, and each of these shaft components will have a different curve. So we'll actually have a family of curves like this. And each shaft component has a curve that says the more times you cycle it, the smaller that magnitude of that torque can be. It's just it's a stress lifetime curve, okay? At some point down here, over on the far left side here, we get into the realm of millions of cycles and infinite number of cycles. Depending on the material, usually I think for steel, this will flatten out eventually. So that's a flat line, and we could call that an endurance curve or a high cycle fatigue limit, which means that you can basically rock it back and forth forever, as many times as you like, and the steel is not going to fail. I think aluminum, it never stops going down. At some point, it will break. But for these machines, there's an endurance limit, basically, and underneath that, maybe, I don't know what that number is. Turns out it's very hard to get this number, but let's make up a number. Okay, so for the record, I'm making up this number. It's not a real number. Let's say 0.1 per unit torque. Okay, so at some point, Teams, shut that Teams off. Okay, at some point, this machine can handle an infinite number of oscillations. So if we're going to do a study, if we have a load that's moving up and down, and we want to know is this going to eventually damage a shaft, a synchronous machine shaft, we can do an EMT simulation. We have to use EMT because it's not 60 hertz, it's all kinds of frequencies. We need to model a detailed version of the synchronous machine shaft. So we need what's called a multi-mass model, where we have all the shafts and all the spring constants. And we use various load profiles. And this is where Alex was saying, if you don't know what the load profile is, imagine what the worst one is. We can do that. We can come up with square waves. We can come up with different load profiles that we've seen. We can do whatever we want, but we can use different load profiles to force oscillations at that load location in the grid, and then measure what happens to the torques on the synchronous machine shaft, and then compare those to the endurance limits for the machine, right? We know that this might happen forever. So this might be happening all day long forever, and so we can imagine we have to be on the far right side of this curve, underneath that endurance limit. We can't be up here. We have to be down here, right? So we can measure all the torques and compare them against those SN curves or endurance limit curves, or if we have a criteria, a general criteria, we can compare against a general criteria. So we need the synchronous machine shaft models, we need a range of load profiles, we need a detailed grid model, and we need mechanical and electrical limit data for that machine. So we need those SN curves. And by the way, I don't think you're going to get them. At least right now, you're not going to get them. We used to get those curves when we were doing SSTA studies and SSR studies. The machine manufacturers are pulling in right now. Machine manufacturers don't know exactly what their limits are, I think. Not sure, maybe they do. But in any case, they're reluctant to give you these limit data numbers. Yeah. Yeah, I'm going to talk about that. That they don't give you SN curves? Yeah, I think it is a little bit. I mean, they might have always, in the past, we've done a lot of, like, one of our main types of studies that we do is subsynchronous oscillation studies. And when you're doing an SSTA study, which is a torsional amplification study, that's when you have a series capacitor near your system. But what you're interested in is if you do sharp impacts on the system, like faults, and you have a resonance in your system, the system tends to ring down instead of quickly, damping. It rings down, and if that ringing is at a torsional frequency, it hits that SN curve. So you get a certain number of cycles of that ringing that can overlap the SN curve, and so you have to decide if that's okay or not. And we've done those studies before, and in order to do that, we get the SN curves. Now, for this application, we're really not interested in that part of the SN curve. We're interested in the bottom part, or extrapolating that out forever and finding an endurance curve. Those curves, I've never actually seen one. I know they exist, but when we push vendors, and even with significant amount of leverage from generator owners, I know there's generator owners in the room who have leaned on their OEMs for this kind of data to try and help them design a plant. It seems to be they're not giving it up. They don't want, and we're not entirely sure why. And I'll keep my opinions to myself on what call it. It seems to be hard to get. Yeah. You basically only need the bottom part of it. If the torques measured on your shaft are underneath that when driven by all these different oscillations, you should be fine. Sorry again? Yeah, you have to be careful with the translation from electrical to mechanical. But if you're thinking about RMS, if it goes above this curve once or twice, then you're into this part of the curve here. If you're going to assume that it's going to go above that curve an infinite number of times, so in the next 20 years, then you have to stay under this part over here and actually stay underneath it. But this is going to bring up, let me go a little further in, because now we're going to talk about what this looks like. Okay, so in a few weeks ago, we did a presentation for the ERCOT LLWG. ERCOT is very interested in this and quite worried about this. And so they hired us to do a bit of exploratory study, and we're still working with them to think about requirements and things. But this is the thing what we were presenting. And imagine on the top left here, I'm trying to make this a little bigger. Top left here, we have a test system, and this is intended to be kind of for science, right? We're using generic data, and we're trying to come up with a system that is reflecting most situations in the grid. So we have a load on the left, transformer, collector, transformer, and then we have an impedance towards an infinite grid and a split to another impedance and a synchronous machine. So by varying these impedances, ZG and ZM, excuse my Canadian, we can basically mimic a machine that's far away or close, or even co-located and disconnected from the grid if we make this ZG really high. By the way, do you want to hear a Canadian joke? One day, Canadians are going to be so powerful that we're going to take over the world. And then you'll all be sorry. All right. So what we've done here is we've basically picked a couple of machine or load profiles. So trying to find the worst cases. So there were two jokes in there in case you got that. I'm really sorry for that joke. Okay, so thank you. All right, so we're using two different load profiles that we think we are going to capture kind of both the worst cases and maybe the probable cases. Okay, so the first load profile is a fixed frequency square wave that we can vary the frequency of. So we're going to use, by the way, there's a torsional mode. We selected the machine shaft multi-mass system so that it has a torsional mode of 12 hertz. Okay, just a typical torsional mode. So this has a multi-mass system on it in the model. Bunch of masses here. Ah, oh, man, terrible drawing. Just erase it. So we can do 2 hertz, which would be an off, or we could do 1.5 hertz, which is machine mode, or we could do 12 hertz, which is a torsional mode. The second profile of load will be what we've seen published in a paper, which is just kind of like what I drew, okay? But it's a fairly low frequency one. I think the dips are every 10 seconds or something. So this is basically, we took the recording straight out of a public paper and put it on there. And that's a pretty good representation of what we've seen, although the frequency is a little lower, I would say, than what we've seen in some of our other recordings. Okay, so what we're going to do is measure the split of active power between the system and the load with various impedances, and we're going to measure what the torques look like on this synchronous machine shaft. So here's kind of the summary of what happened. You can go and look at all the results and the studies and everything. But if you look on the top left-hand side, you can see this load profile that we talked about. So this is a measured. This is again just a reproduction of a published load profile with one small change. We've added a 5% only on the uptime. Like on the high load period, we've added a 5% 12 hertz oscillation. Okay, so that's right at a torsional mode as a test signal. And what you can see here is that we have we have two different shaft sections, so we have three masses, two different shaft sections. We start with 1 per unit, and then these torques grow up to another full 100% on top of that. And then they continuously do that. So we're getting an extra, basically 1 per unit torque added to the existing torque. So 100% torque amplification for a load profile that isn't wild. Okay, this is not out of the realm of possibility. So that's this number here along the bottom. We say load profile 2 with 12 hertz oscillations added to it. We get this amplification. If you pick a square wave and you make the whole variation, so we're going 25% to 100% at 12 hertz square wave, which nobody will say that they will never do. Okay, at least so far we're not getting people to say they won't do that. So this is theoretically possible. Then you get a 5 times split. And this is with, by the way, about a 2/3 split. So this impedance allows about a third of the power to flow into the synchronous machine. So just setting this ZG and ZM so that it splits about 2/3, 1/3. So that's already not a crazy split. We could make this 100% into the synchronous machine, and then everything would be 3 times larger. Okay, so 5 per unit torque, if we assume this worst case, is 100% going to break your machine. Okay, pretty quickly. So if we think this is real, this load profile, S5, load profile 1 at 12 hertz, square wave at 12 hertz going from 25% to 100%, you will 100% break your machines. Okay, so I don't know how to say that stronger. It becomes a little bit of a question of, is that real or not, right? If it is real, and my opinion is we haven't seen a profile that looks like that, and I doubt that we will. It seems unlikely. But this is going to raise some philosophical problems for requirements for us, right? If you think that's a real thing, or if it's a possible thing, do you have to write a requirement to avoid that or to mitigate that? Because that will be a very, very difficult mitigation. That's a very flat load. Okay, so that said, we have loads connecting with this kind of training profile with no requirements. We don't know if they're going to do this or not. So this will be an exciting couple of years. Okay, I really hope we don't see a problem, but it's possible. But even the one that is a little bit more likely, this recorded value, if you add some subsynchronous portion on the top, you have a chance to fatigue the shaft. And if it's not 5 per unit, but it's 0.5 per unit, now you're into the fatigue region of that SN curve. You won't see a failure right away. You'll see it after a certain number of cycles. So you might start to see generators failing early rather than failing immediately. So if you have 6 shafts, you can just imagine this test system. You could take this synchronous machine that's currently 100 megawatts and split it into 10 megawatt machines. Everything just stays the same in per unit. Okay, you just get the same impedance split. You get a tenth of that power goes into a machine tenth the size. It's in 1 per unit. You get the same per unit shaft impact. Yeah, it's a good question. Yeah. Right. So this is something we can see in this test system. In this one, we had this split. They're not ultra low frequency, so they do not necessarily travel too far, but it's very studyable. So in the studies we've done for utilities, I don't have a number for you how far they travel. It's going to depend on the magnitude and depend on the impedance and depend on the split and everything like that. But they do travel to some extent. It's not ultra high frequency. So if you're worried about 1.5 hertz, it travels pretty far. That's a machine. If it's 12 hertz, it will not be as far. But so that's a good question. So the question from Amir was Amir? Oh yeah, for some reason my second guessed that. In this case, we have a 12 hertz mode on this machine, but there may be multiple machines with multiple torsional modes, which is correct. We saw a presentation, actually the same week we did the ERCOT LLWG presentation, we saw GE. Dustin gave a presentation on GE's analysis of this. So as a synchronous machine vendor, they came around to a very similar conclusion, except their solution was just make sure your load has a notch that has 0 oscillations at the modal frequency, which is nice. 0 is a nice number to have. If I never had any 12 hertz component, then I get numbers much lower, right? This one, load profile 2, S9, I get 4%, which maybe is enough to be not worried, I don't know. But so if you just notch out all of the 12 hertz out of the load, you fix the problem. But there's a couple of problems. One is that we don't know necessarily what all the torsional modes are in the system now or will be in the future with all of the generators in the region. And the second thing is, like we already said, the loads don't know what they're going to do. They don't have a built-in, at least right now, they don't have a built-in filter that says we're never going to produce 12 hertz. They're going to produce what they produce. They don't know what's coming, right? So this is sort of adding to the concern. Yeah.
Is there any discussion if the goal is to keep the grid safe? Is there discussion around creating microgrids for just the data centers?
Sure. So this is, you know, what a lot of folks are talking about. So if you want to do, we can use this same test system here. Let's just make this a microgrid and take that system out of the loop. Now you have 100% interaction factor or radiality factor with that synchronous machine. So everything that happens to the load happens immediately to the synchronous machine. So have you made it worse or better for the synchronous machine? Much worse for the synchronous machine, but you made it a lot better for the grid because the grid is gone, right? So one of the answers to this is, yeah, please take your system off the grid. And then, you know, good luck to you. That's a little bit cynical, but I think, you know, it's important to recognize that that is better for the grid, but probably much worse for the synchronous generator because now you don't have that split of impedances between the synchronous generator and the load or and the system. So some study challenges with this. One is that data is very hard to get for the load. We kind of talked about that. What we can ask for is limits on the load variation. We can ask for harmonic profiles. We can ask to a sufficiently sort of sophisticated load, what is the roll off of your load? So there is a filtering effect that happens from the UPSs and the power supplies that mean that certain higher frequencies are not going to get through, right? Is that frequency 40 hertz? Is it 10 hertz? That might matter for some of these things we're talking about. Or if there's a roll off, maybe there's enough degradation of that oscillation that it actually, is less bad than we thought. It's also very hard to get ride-through capability for the loads. Data is very hard or impossible to get for synchronous machines. So multi-mass data you may be able to get, I would say that model, so you can at least look at what the torques look like, but the physical design limits are very hard to get. And the studies require now specialist EMT study capability. So it's not traditional one, it's more like you have to be an SSO specialist. Okay, yes, before we leave the machine impact. It's a good question. And we'll have a little bit more discussion on the different types of studies you might be interested in. But so far, renewable plants, other than, than large changes. So if you're dropping off and the voltage really moves, basically if your system is having trouble because of VAR adequacy or some of these other problems we've had, very high voltages, for example, if you reject the load and you get an overvoltage transient, we could definitely cause ride-through problems for renewable plants. But the steady state variation, I'm trying to imagine ways that could realistically cause a problem for an IBR plant. And I think it's unlikely. It's possible. But if the voltage is moving a little bit, a wind farm isn't going to mind that, as long as it's not driving, weirdly driving some controller mode or something like that. It seems unlikely that it will be a problem. I'm more worried about the big changes that will impact voltage, because the IBR plants can be a little sensitive to over voltage and under voltage.
I think the only other consideration would be like type 1 through 3 wind.
The old ones or the type 3s.
Yeah. But then it's not, I don't think we're seeing like then the cell's not going to blow up, right? It's probably more in the world of like slightly reducing life, right? Because the resonance could change the speed of the speed that you're spinning when the wind is still
maybe
spinning.
A little bit of
so it could be a little bit extra stress, but I don't see it.
Yeah, that's a good point. I mean, if you have a type 3 wind turbine, it's got a mechanical, we didn't get into that in this course, but you have a mix of electrical interface to the grid and mechanical interface to the rotor of the synchronous machine, of the let's call it induction machine, asynchronous machine, whatever. And that we'll see some of those currents showing up on there. So you can get maybe some gearbox wear or something. I think that
a little bit of extra temperature maybe, but and type 1 and 2 wind are directly connected.
Yeah.
Without the power electronics interface, but those are going away anyway. So
yeah, it's a good question.
Left.
I think it's a good question and not something we can write off, but it might fall a little further down the list of like fires that we're trying to put out. Let's put it that way. Okay, we can come back to this, but let's move on. What time is it? Okay. So we're also worried about flicker, right? I would say this is less of a, synchronous machine shaft breaking kind of problem and more of, your operators are going to be getting calls from customers kind of problem, which may or may not be a problem for you. I think right now, any of you who have worked in, sort of having to deal with flicker issues realize that the flicker standards are a little bit out of date, or at least are based on older incandescent technology where you have, a certain change in voltage will cause a certain change in perceptible light in incandescent lights. And if you get to a certain frequency and a certain variation of voltage, it will start to be annoying. The problem is now we're not using incandescent lights. We're using LEDs of widely varying quality of converters. And so if you flick the voltage by 2% or 5% or 10%, it might be a different threshold before the LED just is completely flat or goes off and comes back on. And so we've seen mitigation for these things, including for large loads. The large load does cause a flicker problem in LEDs. And then the solution is you go and just change all all of the lights to a higher quality LED. But what voltage was that? It's really a little hard to do a flicker study based on the old standards because we don't really know what for that region is going to be a problem. But it is something that's not that hard to study, and it's also maybe not that hard to mitigate.
One part about that, so one of the new LED lights, basically what causes visible flicker is not the flicker, not in the traditional sense, but the harmonics that will translate into flicker in the LED lights.
It can be harmonics, but it can also just be a voltage dip. If you dip the voltage, the light will go off and come back on.
Also like the harmonics, will cause flicker.
Yep. Yep. Harmonics is a separate problem. I'll get to it. And actually, you can come up and teach that part. Just joking. I'm teasing him here because he's actually a genuine expert on harmonics, and I'm not. So, okay. So, data required for this type of studies for flicker will be the synchronous machine. Oh, this is wrong. Sorry. You don't need that. You will need the range on the load profile, how much it can move, basically. You will be interested in ramp rates, and ramp rates is something you can also derive from that frequency bandpass that I was talking about. So they're not truly square waves, right? We don't have real square waves in the world. Probably we have some very fast ramp rate, and that ramp rate might matter for flicker. And measurements are useful, right? There's different ways we can do these flicker studies. We can do it using simulated flicker meters and EMT, but there may also be simpler ways to study this in just using power flow studies. You can't exactly just do a change in load and resolve the case and measure the voltage, although it's almost that simple. You have to take care that you're imagining the subtransient time frame. So that might mean you have to lock the voltages and angles of your synchronous machines before you do your new power flow solution. And for renewable plants, grid following plants, you have to lock the P and the Q. Okay, but if you can do that, you can do that in a script, then you can actually do this study in power flow, potentially. Okay, which is nice. Any study we can do in power flow, we like.
I'm curious, have you seen there's a lot of customers that don't necessarily know the load from
Right. Yeah.
Would they even have this kind of information?
Well, the nice thing about this study is that if you're just worried about how the voltage change might impact the lights, you can just imagine one voltage change and then say it's going to happen a bunch. So if you just imagine a single square wave or a single step change, that's you can do a before and after in power flow. So it doesn't really matter what the final load profile looks like. You're just worried about the worst case step, right? So frequency, again, you could imagine it's 8 hertz, which is, I think, the low point on a flicker curve, something like that. So just imagine what the most annoying frequency is and do that. I think it's 8 hertz. Harmonics. So harmonic, first of all, to do a harmonic study, you need to know what the harmonic characteristics of that load are, and that's not a trivial problem. Oh, yeah, we're good on time, right? Before our break. So it's not a trivial problem to calculate what those harmonics are. You can do it in basically 2 ways. You can have an extremely detailed EMT model, like the one we talked about yesterday, but now with the switching included, for every device within the load. Okay? That's going to be a challenge right now for you to get. Although it is coming. We'll talk about models in a bit. Or more likely, you're going to measure this in a lab. So you get harmonic measurements from each of the components in the load from a lab, and then they can give you an aggregated model of the load for harmonic purposes. There have been events recorded of large harmonics associated with data centers. So this isn't something we can ignore. It's probably a real problem in some cases. But the interesting thing about this, from the harmonic studies we've been a part of, is that at least for one, we've done only a couple. For one of these, very large loads where we had good data, we had good harmonic models, the load itself in this case was not a significant source of problematic harmonics. But it was so large that the utility added a lot of capacitors in the system to compensate for the VAR losses for that load. So this is just power flow outcome. They added a lot more shunt caps, and different combinations of those shunt caps drove system harmonic resonances to 5th and 7th, which meant we had a large harmonic amplification problem at 5th and 7th as a result of the capacitors, which were a result of the load. Okay, so just another caution with shunt capacitors: the more you add, the more likely you are to start occasionally hitting bad harmonic amplifications at problematic harmonic frequencies. So we need them to produce a frequency-dependent Norton equivalent source, which turns out to be a little bit hard to do. You can use perturbation techniques to derive impedances, and currents can be measured in strong test beds. For those who are actually interested in harmonics, so Amir, one of the problems we've had with this, a practical problem, and this actually is a practical problem with what's recommended in IEEE 2800, is that trying to do these frequency scans or trying to measure the harmonic impedances of the devices is very hard if the impedance is time varying in the device, which it turned out to be in some cases. So if it has a constant impedance at some frequency, we can measure that and use it in the study. But if it turns out some of these power supplies, for example, actually their impedances are varying with time, which means we can't measure them properly. Somehow the load was able to overcome that in their lab. So then you do frequency-dependent characterization for the external system. So you do frequency scans of the external system, you add your harmonic sources, and then we do a multi-port harmonic power flow. So this is sort of a very special study. You can calculate also the some representation of the background harmonics. You can use a distributed background harmonic model, put it into your power flow, and calculate whether there's going to be a harmonic amplification problem or not. So it's a sort of a specialist study, something to think about though. Active power variation studies, and you'll notice there's a theme here: you need data, right? You need modeling data to do these studies properly. So machine mode oscillations and inter-area oscillations, we can use phasor domain tools for this. So if you have a PSSE model or another phasor domain tool, you can build a load model that oscillates at whatever frequency you're worried about, let's say 1.5 hertz, and drive it at that frequency and see what the amplification looks like in your power system. Yeah, I won't say much more about that. This might turn into be an interesting problem, and the same thing can be done for inter-area oscillations. Although historically we're very bad at doing inter-area studies. I saw a good paper lately. Somebody out of it was one of the national labs came up with an idea for looking at inter-area oscillations for loads. So I think people are thinking about it. I don't really know how to do this study properly. I'm not sure very many studies are done on inter-area oscillations. So hopefully we figure that out.